So this was an issue in the book. If this was on that gold example, so the issue was 5 bonds broken, right? So this was talking about these different size gold particles. I can't even remember. This was a homework. This was assigned? No. Okay. So if you're reading in the book, just make a note. This is example. This is a question in the book on page, or on Andrea Tao chapter, page 14 and 15. So if you're just studying in general, be aware that there's an issue here. Here, this is correct. It's talking about a face-centered cubic example, and it says there's 5 bonds broken per surface area, 7 adjacent nearest neighbors, okay? But then it's talking here about a gold 13 cluster, okay? And so this should be 5 times 12 equals 60 bonds, whereas for whatever reason it's 5 times 7 here, okay? And then down here on this table, this should be switched. There should be 5 bonds broken and 7 nearest neighbors, okay? Okay, yeah.
How does the nearest neighbors affect our energy again?
Well, what do you think? How does bonds broken affect?
It takes more energy to break the bonds given more near neighbors.
No, but your original question was in terms of how does it affect the surface energy?
More neighbors equals more passivity in the surface.
A more stabilized surface if you have more nearest neighbors. More broken bonds equals a less stable surface.
Okay.
Yeah. Yeah.
So you said the broken is correct for 5 FCC, but then on page 17 to your right instead for the FCC unit cell number of bonds broken is 4.
For which plane?
Because
it changes by plane. And we're going to walk through that a little bit more because I think there was some generalized dissatisfaction over the, oh, my speaker isn't on. Yes.
So going over the homework summary, just trying to
Yeah.
question number 2.
Yeah.
The chart for the initial drug.
Alpha, beta, gamma, delta? Okay. So for a 1, 0, I mean, the answer is 4, 5, and 3 for 1, 1, 0, 1, 1, I'm sorry, 1, 0, 0, 1, 1, 0, and 1, 1, 1. But I just want to walk through it a little bit more. This, I think, is one way, this is one way of looking at it where the shape, the white ones are bonds that have been broken. Imagine that we're putting a plane through here into the board. Okay? And so these then are the remaining nearest neighbors. So the most stable one is 1, 1, 1, right? Because it has the most remaining neighbors. Okay? So where's my remote? I did some screenshots from this guy. One made it, I think it's almost easier maybe to think about it in terms of how many are remaining and then subtract, as opposed to try to visualize how many are lost. So there should be 12 in a perfect, the center of this crystal, it should have 12 nearest neighbors, right? How many should it have it in BCC? 8, yep. How many in simple cubic? 6. How many in body center cubic? 8. So you're starting with 12. And so to think about how, imagine this one right here. So how many does it have touching it still? 1, 2, 3, 4, right? But then you have to think about the plane below it. And so that's where the other 4 come from. Okay, so it's resting on 2 there and 2 there, right? Maybe if you see it, if you look at it kind of like there, you can see that it's resting on these 2, and if there was another plane forward, there would be another 2. So 4 that it's resting on, and 4 on the same plane as itself. So that's the 4 plus the 4 that are remaining, right? This 4 and these 4, right? These 4 right here are the 1, 2, 3, 4. Okay, and then there's 4 below it. So we know that we still have 8 remaining, so we must have lost 4 broken bonds. Okay. Now, let's look at this one, the 1, 1, 0 plane of this same material, right? It still has 12 nearest neighbors in a perfect crystal, but we're just looking at it through a different slice through this crystal. Okay? So here, in this plane, it has 1 on either side. So that's these red ones, right? It's, again, resting on 4. 1, 2, 3, 4. Just like the last one, it was sitting in a little cup of 4. And it has 1 directly below it. Okay? So that's what this is showing you here. The 2 on either side, the 4 that it's resting on, and the 1 directly below it. Okay? So you still have, you have 7 nearest neighbors, so you lost 5. Okay? One thing that's confusing is in your book, it has 5 parentheses 6. The 6th bond is difficult to find. Okay? So this is from your big book. So I think what they mean here is that because of the way this plane sits, that this one of the adjacent plane below kind of acts as a nearest neighbor. So if you're curious what that 5 parentheses 6 means, I think that's what it means, but we're just going to stick with it being 5, right? Okay? Okay. 5 lost in a 110 for an FCC. This one, now, of the 111 plane, this part's really easy. The 6 that it's sitting on next, there are 6 neighbors in the same plane. 1, 2, 3, 4, 5, 6, right? And then maybe if you look at this one, you can kind of imagine how there's 1, 2, and then there would be a 3rd one right there that it would be resting on. So if that's hard to see, hopefully this one's easier. So you have 6 remaining in the same plane, 3 below that is 9, so meaning you lost 3. Okay? So let's derive then a little bit more the planar atomic density, because I just threw that table up there last time and didn't talk about it nearly as much. So we remember that our binding energy is 2 times the enthalpy of sublimation, which we can look up, times Avogadro's number and Z, right? That's the binding energy. And that our surface energy is surface energy is a function of the number of bonds broken times the binding energy times this planar atomic density. Okay, so let's go through this for these 3 cases. In a FCC crystal. So for a 111, how many atoms do we have in the 100 plane? 2, right? So this is our 100 plane, right? So if we were looking on that side of the plane, there's this whole one, and then 4/4. Okay? Right? This is, I think, a better way to see it. We're looking at that side of the unit cell. Okay? So we have, and I'm sorry, I didn't do a very good job of explaining that. Planar atomic density then is just the number of atoms per, what's the right way, per this like selected area of unit cell. So for here, we're always going to have the unit area be, what do you think? A squared, right? So here, the number of atoms for FCC 100 is 1 plus 4 times 1/4 over A squared, 2 over A squared. Now, what about our surface energy expression? God, I cannot make that little gamma to save my life. FCC 100 equals 1/2 times number of bonds broken. Here we said is 4 times our binding energy times 2 over A squared. Equals, so this is a very generic expression then that we can use for any type of FCC crystal that we're looking through a 100 plane. So did we get it right? Let's go back to our table. Yes, 2 over A squared for the planar atomic density. And there's our expression for surface energy, 4 times the binding energy over A squared. Okay? Let's try it again for the next plane. Okay, how many atoms do we have in that plane? First of all, what's the plane look like? The 1, 1, 0. Diagonal, kind of all, right? So it's going to be the plane that goes from that corner to that corner down into it. Okay? So how many do you think that's going to be? It's 2 again. But here, the way it's constructed is slightly different, right? So here we have, well, we have 2 times 1/2 plus 4 times 1/4. Okay? Now, what's the area? We're looking at the area of this plane. Right? Does everybody see that? You've got, this is A, so therefore that's root 2A. Okay? Because we're looking at that, what I'm saying is that's A, so that's root 2A. Okay? So therefore, our overall density is going to be 2 over A times square root of 2 of A, which simplifies to root 2 over A squared. Right? And so then to do this, yeah. Equals 1/2 times number of bonds broken is 5. God. Times the binding energy times root 2 over A squared. Right? I'm just using that equation right there that I put. So therefore, this is simplifies to 5 over root 2 okay? Yes?
Just based on the chart that we have for 0 plane.
Based on this, right? So we still have 7 nearest neighbors. 1, 2, 1, 2, 3, 4, plus 1 directly below. So we still have 7 nearest neighbors, meaning we had 5 bonds broken. Okay? Okay. Yes.
Will you be posting this PowerPoint before our break?
I'll do it today. Now, here in your book, so they wrote 5, and also maybe you can think about it as 6. So when they teased this out, they used the 6 here. Okay, instead of the 5, we're gonna use this. Yeah. This is way more right to me. Yeah. Okay. I gave that one away. Damn. Okay, what about the 1, 1, 1 plane? Triangle. Yes. 1, 1, 1. Okay. So remember, 1, 1, 1, the reason it's a triangle is because we go to 1 on the x plane, 1 on the y plane, and 1 on the z plane. Okay? And so if you put a plane through that, it would look like this. Okay? So the number of atoms is what? No, it's 2 again. And because this is, you've got 3 halves and 3 sixths. So 3 times 1/2 plus 3 times 1/6 equals 2. Now, what's the area? This one's a mess.
Root 2a plus 5a divided by 2.
So the area of a triangle is 1/2 base times height. So we know what base is, right? Base is root 2a. Now, height, we kind of need to, when I first looked at this, I really wanted to argue with the truth and say that it was just a, right? Because you can kind of imagine that it's this, like that's a, back behind the triangle, but the triangle's leaning, right? So it's not a. So we kind of have to look at it like this, okay? So this side right here, the hypotenuse, is this, which we know is also root 2a. Then what's this? Half of root 2 times a, right? Because this we also said is root 2, but it's just divided by 2. Now, this is our unknown, right? So this is now right? Oops. Tell me this is right, because I think the book is wrong on this, and I'm really certain of it, right? Because this would be 2 equals that squared times that squared is clearly that, right? Yeah. Right? Yeah. Okay. So then this cancels.
I think that there's shouldn't the denominator just be 2 and not radical 2? Because you have x squared equals 3/4, and then x squared, that you get square root of 3 over 2, not square root of 1b3 half.
No, it's square root of 3 halves. It's square root of 3 halves. You gotta get it inferred. You gotta get it for x is correct.
Right?
It's a phase into the triangle.
Oh, okay.
It should just be the shortest.
Right.
This is right?
Yeah.
Okay, because okay, so that cancels, and this gives you square root of 3 over 2 times a. Now, this is just the area that we calculated, right? We still don't have our planar atomic density. So our planar atomic density then is 2 over, yeah.
Oh yeah.
Area. Yes. Okay. Now the reason the book is wrong because they have the numerator denominator messed up. So that's why I put this in red. Okay. See, they have it written as this is like what's so frustrating. Like once you get into graduate school and beyond, like when you're an undergraduate, you just like everything is right, right? But like in my world, like I'm always reading these manuscripts and I know like half of the time they're completely full of shit, right? And so like this is what's really frustrating is when you have to like really use your critical thinking and be like, okay, these people are experts, but they messed up, right? And so welcome to my world. Welcome to what your life is going to continue to be like, where you can't trust anything you read. I'm sorry, why isn't my a squared what? Yeah, it should be. Okay. Now we can finally go and calculate our surface energy for FCC111. Number of bonds broken is 3 times our binding energy times the planar packing density. Okay. So we can do some stuff there with those 2 3s and that. And they got that part right, right? So that's why I was really sure that that was just a typo, because that part is right. Okay, so hopefully that's more satisfying than just throwing that table up there. Okay? So now we're going to switch to, well, I mean, of course you could do the same thing for a BCC, right? And then you could start to even actually calculate this for things like the actual numbers, right? So if you had the number for chromium, you could start to actually calculate which has more, which plane has a higher packing density. Yeah.
If you're given like Miller indices like 5, 3, 2, we would just decompose and apply the same formula like 1, 0, 0, 1, 1.
Yeah, so you would break that down and tell you how many. See, those become particularly hard because calculating the number of broken bonds, you're going to use a decomposition into those subunits. Yeah. Yeah.
So like how many broken bonds for BCC for 111 plane?
BCC for 111 plane. Didn't we decide that was 4?
Oh, that was for SC7. 4 is for 100.
Yeah, but I think it's also the same for.
Yeah.
What was? So for BCC 100, was that your question or 110? Okay, we're on the same page that it's 4 there. I think I have a slide on this. Some people are just savants at crystallography savants, and can just see. I have to see it to get it. By inspection, yeah, that's the one that always gets. On inspection, it is obvious. Okay. Yeah, but number 6 is hard to find. Yeah. Okay. So BCC 110, why?
Is this taking the plane and making it in plane with the board?
No, I think the plane is here.
That's what it's doing.
Yeah, this is contradicting what I. Let me get back to that. We'll give a definitive answer for the BCC system next time, but for now I'm very confident on the FCC system. Okay. So this was all talking about surface energies of stuff, right? But mostly solids because they're crystals. But what if we have liquids? And so what we're going to talk about is the Young-Laplace equation, where we have these differences between an old surface and a new surface. And there's pressure inside and pressure outside, okay? And how these stabilize. So maybe I should jump to the point about like why you should care. So you've seen Ostwald ripening before? So have you seen these kinds of images before? Okay, no, some yes. So what nanoparticles do is that there's this tendency for big ones to grow preferentially at the expense of smaller ones. So this is a mixture of platinum nanoparticles. And so there's really small ones, maybe 1, 2, 3 nanometers, and then these bigger ones that are closer to 50. And these are at 4 different time points. So like day 1, day 3, day 7, and maybe day 30, okay? And what happens over time is that the bigger ones become bigger and the smaller ones essentially disappear. And so there's 2 mechanisms that this can be through based, and it's a function of the material and the crystal structure, but you either have dissolution back into monomers and then the monomers redeposit on your surface, or there can be physical kind of aggregation, okay? So you've probably seen this in something like soap, right? And why can't I make this play? Can't. Anyway, you've seen soap bubbles where you have a bunch of small ones and they come together and make bigger and bigger and bigger soap bubbles, right? The other example that is common is when you have ice cream, and ice cream, you know, when it gets really old, it is kind of crunchy, and that's ice crystals inside of it because ice cream has ice or frozen water in it, right? But over time, those frozen water crystals come together and make bigger and bigger and bigger ice crystals, okay? So what do you think has more pressure on the surface or a higher surface energy? The smaller ones, right? Because therefore they're less energetically favored. Okay, so how much exactly, right? So that's what we're going to talk about. Okay, so imagine that we have a system like this where we have our old surface and then we have a new surface as there's a change in pressure either on the inside or the outside, right? So if we're having an increasing pressure on the outside, then it's going to become smaller or vice versa, right? Okay, so talk about the overall work on this system is going to be the surface energy times the area, okay? And just to remind you here, this is units of newtons per meter, and this is going to be units of meters squared, which is going to give us Newton meters, which is joules, right? So that's good that that works. So then our change here is going to be the change in work is going to be a function of the change in area. Okay? So then we can kind of more carefully define this as x plus dx okay, so old or new versus old. Okay. So multiply this out, x dy, y dx. Okay, and we can see that this cancels. And what do you think we can assume is small? Dx dy we can assume is small. So then our change in work is going to just be this, x dy plus y dx. Okay, we'll come back to that. And we can go back to thinking about pressure and volume being a similar kind of work, right? And kind of being responsible for these changes, right? We're saying that the change here, the change in volume, is due to change in pressure, or vice versa. What this is saying is that it's not due to some kind of change in like temperature or ionic strength or concentration. Okay? So here we're going to have some kind of delta P times dV also equaling this, our surface energy times our change in area. Okay, we're just writing a different expression for this because we did one over there. Okay, and here just our units are what? Newtons per meter squared times meters cubed, which again gives us Newton meters, is joules. Okay, yeah.
What is that top equation? Is it dV is equal to negative delta V?
No, I'm sorry. This was just, I'm just saying that this was not an expression. This was me thinking out loud. What it's saying is that we're talking about pressure and volume work on our system. So we're saying that a change in volume is due to a change in pressure or vice versa, right? This, well, no, it's specifically equal to our change in our surface energy times the change in area. Yeah.
So where does dz come from?
dz is coming. Hang tight. Yes. This is, yeah, this is squared. Newtons meters squared. Okay. So how can we, well, so okay, so where do you think the dz comes in then? Yes, right? So what do you think this change in volume then is going to be delta P x, y, dz, right? And now we can set this expression equal to what we determined this to be here, okay?
we don't have to do the same thing with dV that we did over here with dA?
We did. That's what this is.
So that'll be
X, Y times dz.
We're doing x plus dx times y plus dy times z.
No, because that we were calculating area. This is now our change in our volume. So X, Y, Z.
So why do we ignore dx dy?
Okay, why do, because we're assuming that that is small relative to our change in dz and the volume. Yes, good question. Okay, so then we can rearrange this a little bit. Equals. Okay, so we just divided that by that and that. Yeah. dy over y. Thank you. Y dz, x over x dz. Yes. Now, the next assumption is kind of, see if you'll believe me. This is showing the same thing in kind of a different way. Right? So if we assume that these kind of look like triangles, then we can kind of assume that the ratio of y to dy this ratio, that's y plus dy, and that's y, is equal to the ratio of this, R2 over R2 plus dz. Does that make sense, that those ratios would hold?
Sufficiently small.
At a sufficiently small alpha, yeah, or theta. Okay, so then if we redefine this, okay, what's going to, this will cancel, and or 1 over r squared is dy over y dz. Which is what we want, well, what we have over here, which is this, right? dy over y dz, yes. So this then leads to the overall Young-Laplace equation. R2, well, it's additive, so it doesn't make any difference.
And that's a gamma, right? And a y.
Thank you.
Thank you.
Okay, so because if we then did this for, Same thing. dx over x dz. And that would have come from x plus dx equals r1 plus dz. And solving for r1. Yeah.
So did we just say that the change in pressure is equal to the original, the initial radii? Isn't that, I mean, the additive of 1 over the initial radii? Assuming the...
No, it's these two radii.
Right.
Radii 1 and radii 2.
The x and radii and the y. And those are both still initial quantities, aren't they?
Say your question again.
So R1 and R2 are based on the original x and y.
Yes.
So we just said that the change in pressure is equal to the surface tension times the initial radii. I mean, they're
And the end radii.
But I think
Aren't they
we're looking at like those two radii are both like independent of DC, which is what is actually like the part that's being modified by the pressure.
So R1 is related to x initial and R2 is related to y initial.
Yeah, because R2, okay, so R2, you're saying R2 is essentially R1 plus DZ.
No, R2 is y, right? R2 is just the initial radius on the y curvature.
Yes.
And then R1 is the initial of the x curvature. So they're both just initial.
Oh, are you saying, so you're saying should they be exactly the same?
No, I'm saying we have a delta p, but that's a change, but then we're relating it only to the initial values of r.
Aren't
the
they
x and y
constants? They
curvature.
don't change based on the...
I don't see why this is not the end curvature.
Make sure it's not.
Because that
Isn't
curvature
that-
is R1 plus D.
Isn't that the initial position? On that diagram, the dark line, right, is the initial position. So R2 just points.
Oh, yeah.
I mean, if that's what it is, I'll accept it for now.
Let me, no. I mean, what this is the old versus the new
Right.
pressure.
It's supposed to be
But
R.
somehow this we got two R1s and two R1s and
Right.
R2s.
But
Yeah. Hang on. We'll clarify that. Yeah. That's probably a good stopping point. We'll pick up right there. Okay.